Okay, let's do what we always do and greet each other properly. Good morning.
Good morning.
All right, this is Mr. Ainsworth. We're going to get into what's called implicit differentiation today, our last differentiation technique. And we're going to learn to solve all kinds of variety of problems. Now take a look at what I have written up top here, at the top of my lesson here. Some functions, and there's a couple examples at the very top. Some functions are written what are called explicitly in terms of x. This first one, look right here, is one example that's where y is written what's called explicitly in terms of x. Okay, you'll see y isolated basically. When you see a function as y equal to some function of x, we call that an explicit function. And using all the different techniques you know, it's easy to differentiate, fairly easy. However, if you're going to differentiate a function that doesn't have y isolated, which is what's called an implicit function, okay, the question is how are you going to differentiate it? Because all the functions that you've done or dealt with so far have y isolated. You have y equals some function of x. You've only differentiated what are called explicit functions. Today, if you look at the circle right here, where if you notice it's x squared plus y squared equals 25, that's not an explicit function because y is not isolated. So the question is how do you differentiate that without isolating y? Okay, that technique is called implicit differentiation, and that's what you're going to be learning today because many times it's impossible to solve for y. Sometimes it is. In the circle case, piece of cake. We're going to do it actually. But in many cases, like you guys remember those crazy functions called lemniscates? And all those polar functions? When you converted them to rectangular, they're very, very complicated. And it's impossible, even for me, to isolate y and make it explicit. So what you need to do is learn how to what's called implicitly differentiate so you don't have to worry about isolating y. Okay? So what we're going to do is we're going to actually take a look at the circle here. And right now it's this function here, the circle here, x squared plus y squared equals 25. It's an implicit function because y is not isolated. And what we're going to do is we're going to find the slope of the tangent line given the circle there at the point 3 comma negative 4. And we're going to do that by isolating y first, just to do it the only way that you know how so far. And then afterwards I'm going to develop the implicit idea. I'm going to show you how to implicitly differentiate and do it a much easier, much faster way. Okay, and then we'll be doing it that way for the rest of the class. Okay, so everybody, eyes right over here on the left. Suppose that we wish to find the slope of the tangent line at the point 3 comma negative 4. Okay, what we need to do first is write y explicitly as a function of x. That means we need to basically, let's write this down, we need to isolate y. Okay, and that's fairly easy to do in this case. So I'm going to go to the right side. I'm going to take x squared plus y squared equals 25. And we're going to basically isolate the y variable there so we can write it as a function of x because right now it's not. So I'm going to subtract x squared. I get y squared is equal to 25 minus x squared. And then to isolate with y, you got to square root the function. And you get y is equal to plus or minus the square root of 25 minus x squared. Okay, now that's actually two functions. Y equals positive root of 25 minus x squared. And also y could be equal to the negative of that, so negative the root 25 minus x squared. The question is, what does the first function represent in respect to the circle on the graph? What portion of the circle do you think this part represents?
The first half.
What half? The left half, right half, upper half, lower half? Keep in mind that's a y value, right? Say it again. Yeah, this is the upper half. The positive root is the upper half. The negative portion is the lower half. Okay? So let me see. Let's write that down. This is the upper half of the circle. If you later on your own time tonight, go ahead and enter it in on your calculator, your TI-84, and you'll see the upper half only. And then you enter the second function in. You can call it y2, and you'll get the lower half, and you can put those two together. By the way, that's how you graph a circle on your TI-84. You have to isolate the y value, because if you remember in the equation editor on the TI-84, when you enter in functions, they're always y1 equals, and then y2 equals, and then y3 equals. Who remembers what I'm saying? Okay, good. So whenever you want to enter functions, you have to enter in the y variable, which makes it tough on you because, like I said, not all functions you can isolate y. It's impossible sometimes, so you got to know what to do. So when you want to find the slope of the tangent line at 3, negative 4, are you going to differentiate the upper half or lower half?
Lower half.
Lower half, okay? So then that calls for chain rule. Okay, so if you're going to find the slope of the tangent line, we need to evaluate or differentiate the lower half. Okay, I'm not talking with the calculator, we just got to use the chain rule. So we have to rewrite that in exponential terms and do it the only way we know how so far. Okay, you remember, to get the slope of the tangent line at any point, you differentiate the function and then evaluate the derivative at that point. In this case, we're evaluating it at x equals 3 because we want the slope of the tangent line at 3, negative 4. Okay, so let's rewrite y2 as y equals negative of the quantity 25 minus x squared to the 1/2 power. So you can tell that we have an inner function that's equal to 25 minus x squared, and the outer function is the power, the 1/2 power. So we're going to have to use our general power rule here and the chain rule. So we first, by differentiating the outer function, the 1/2 power. So here we go, y prime, or y2 prime, okay, that means the derivative of the second function, okay, is going to be equal to negative 1/2 times something to the negative, well, that's the answer, 1/2 minus 1, or negative 1/2, right?
We're not squaring it.
What do you mean squaring it?
Like y squared equals 25 minus x squared. I would just get something like that. Get you back to the Oh, okay.
No, we don't want to do any squaring business. We just want to differentiate. Because to get the slope of the tangent line, you just differentiate. I'm using the chain rule right now.
Oh, okay.
All right? And then times, we evaluated at the inner function here. And then we have to multiply it by the derivative of the inner function. And what's the derivative of 25 minus y squared? Negative 2x. Okay, now let's rewrite this a little bit, and let's clean it up a little bit. You distribute, or actually just notice the negatives here. When you multiply the negatives, they're going to cancel out. That's going to be one thing, so look in blue there. And then 2x divided by 2, the 2's are going to cancel out. Okay, so you're just going to have x divided by the square root of 25 minus x squared. Because again, the negative 1/2 power just shifts downstairs and then convert to radical form. Give me a thumbs up if you're with me on that. That's just the chain rule, just evaluating the derivative. Now, if you want the slope, you got to evaluate the derivative at the x coordinate of your point. What's our x coordinate?
3.
And what's the x coordinate? 3. So we evaluate this. Look right here at x equals 3. And what do we get? Let's check it out. We get 3 divided by the square root of 25 minus 9. Let's do it out loud. What's 25 minus 9?
16.
Root 16?
4.
So our slope's 3/4. Now look at the graph. Look right here. Look at the tangent line. I'm talking about this one right here. There's your tangent line at that point. That's a computer drawing right there, so it's pretty accurate. That line, does it have positive slope? Give me some head nods or something. Okay, and we should, yeah, it is. It's going to the upper right. So it's got positive slope, and we came up with a positive slope as an answer of positive 3/4. So our answers are making sense. And if you had a grid up there, you'd be able to see it has a rise of 3 and a run of 4. Okay? Now, that was pretty easy because we can isolate y. But what happens if you have a very, very complicated function where it's an implicit function, y is not isolated, and you cannot isolate y? What do you do? Okay? That's what today's lesson is all about. How do you take an implicit function where y is not isolated and differentiate it that way? Okay? So let's learn how to do it another way.
I can put a we know there.
Say it again?
Compliment that, the we know.
Yeah.
Put in there.
Oh, yeah. Well, I know you'd love that, huh? Okay, so I made a little point here. Unfortunately, not every function or every equation involving x and y can be solved explicitly. And what does that mean again?
In terms of
Y is
x.
not isolated.
Yeah, in terms, y in terms of x, okay? So the question is, how do we differentiate it? So let's rely upon what we know about what's called the chain rule. Okay, now the derivative of a composition right here, f of g, is going to be f prime evaluated at g times the derivative of the inside function g prime. So let's review the chain rule just a couple of times, and then I'm going to switch gears a little bit and show you how to handle it in a different case. Notice our inside function here on this first one here is 7x, and the outer function is what? Cosine. So we start differentiating cosine first. Start with the derivative of the outside function. So let's do it together. Derivative of cosine.
Negative sine.
So you get negative sine of the inside function 7x times the derivative of the inside function, which is 7. And then just clean it up, write it, and switch this out in front because you're not multiplying the angle by 7. You're multiplying the whole function by 7. So it's going to be negative 7 times the sine of 7x. Okay, you'll see why I'm just reviewing this in a minute because I'm going to switch to taking the derivative of y, or a function of y, in a minute. Okay, and again, on this next one here, the 4x minus 1 is the inside function. The cube is the outside function. So we start with our power rule. So you start off by taking 3 times something to the 3 minus 1, or second power. Evaluate that at the inner function, 4x minus 1, and then multiply by the derivative of the inside function, which is what? 4. Okay, and then just clean it up a little bit because it's simple in this case. 3 times 4 is 12, so you get 12 times the quantity of 4x minus 1 to the second power. Okay, that was just the chain rule in action a couple times. Now, let's take a look at this. Go ahead and turn the page a little bit. We're going to use the chain rule again, but this time look at the notation and how it's changed a little bit. Okay, now we're going to assume, look right up here that I'm highlighting, we're going to assume that y is a function of x. Big assumption right there. Y is some function of x. Y could be equal to sine x, y could be equal to x squared, y could be equal to any function of x. And in general, what we say is that y is some function of x. So when we differentiate or take the derivative, which in shorthand we take d dx, that's the derivative, of y cubed, we have to assume that this variable y here is not just y, it's actually a function of x. So in reality, y could be equal to sine x or cosine x or tangent x or something weird like x squared plus tangent x. It could be anything. So who sees that we actually have a composition there? Look right here. This is some function of x raised to a power. That's actually a composition, and when that's a composition, you have to kick in what rule? The chain rule. Okay? So again, on the cube function, the cube is the outer function. We're going to start differentiating there, and then differentiate the inside function. Okay, so what we have here is that when we take the derivative of y cubed in respect to x, we're going to have 3 times the inner function to the 3 minus 2, or excuse me, 3 minus 1, which is 2. So 3 times something squared. Evaluate that as the inside function. Now you have to kick in the chain rule. You got to take the derivative of y. And what's the derivative of y in respect to x called, or dy dx? No, you take the derivative of y in respect to x. So let me write it out. Derivative of y in respect to x. Guess what that's called? It's another name of dy dx. Y prime, very good. It's the same thing as y prime. Now, you don't know what y is, so you just call it y prime. So you differentiate the outer function first, and you get 3y squared. And then you take the derivative of y in respect to x, which is simply y prime. So you can rewrite it like this, just 3y squared times y prime. These are the same thing. Now in the previous examples, it wasn't y, it was like, look up here, let me just scroll back up a little bit. Instead of y, it was 4x minus 1. That's a function of x. That's why I said in my assumption is that this right here, this y variable, is some function of x, like it was before. So in general, you just look at the outside function 3. It's a third power. You use your power rule first. You use your power rule, and you get 3y squared. And then look at the inside function. It's y. Take the derivative of y in respect to x, which we call dy dx, or we can call it y prime. And that's your derivative right there, y prime. You need to get used to that. So let's try it again, okay? So we're going to take the derivative of 5y squared. And the first thing you do is you kick in your power rule. You're going to take 5 times 2y to the 2 minus 1. So 5 times 2y to the 2 minus 1, or 1 power, times the derivative of y in respect to x, which you can say is dy dx. Okay, and anytime you see dy dx, that's the same thing as y prime. So if you want, you can clean that up. You can say 10y prime, or 10 times y prime. Excuse me, 10y to the first power. That's not a prime. Let me erase that. It's not good to put a 1 there because it kind of looks like a prime. So 10y times y prime. Okay, and on the third one here, on the derivative of sine of y, you first take the derivative of sine. Okay, so let's go over some basics here. What's the derivative of sine? Okay, so on this one you get cosine of y times the derivative of y in respect to x. So times dy dx there. But anytime you see dy dx, you think y prime. So we're going to have y prime times cosine of y. And again, the reason why I shifted the y prime in front is so that you know that you're not multiplying the angle by your derivative. Okay? Okay. Now the next one involves what rule?
Power rule.
Not just the power rule, but x squared times y to the fourth requires a what? It's a product rule, and the product rule goes first times the second plus second times the. Okay, so this is a product rule right here. Okay, so this one I'm going to write out in detail here. Okay, so we have the first function x squared times the derivative ddx of the second function y to the fourth plus second function y to the fourth times the derivative of x squared. Okay. Okay, so let's handle this one first. Okay, notice we're taking the derivative of y to the fourth, and we're going to assume that y is a what? It's a function of x, so we have a composition here. So that's a chain rule right here. So we're going to have x squared times 4y cubed, there's your power rule, times the derivative of y in respect to x, which we call y prime, plus y to the fourth times the derivative of x squared in respect to x. That's simple. What's the derivative of x squared in respect to x?
2x.
Just 2x. Okay, so times 2x here. And cleaned up just a little bit here, we've got 4x squared y cubed times y prime. Make sure you make that prime on an angle there so it doesn't look like a 1. And then plus 2x y to the fourth. Okay, let's stop here and ask questions before I do anything else. Now let's go back to our circle example. Let's revisit it. And let's take this equation, which is an implicit function, and let's differentiate it implicitly. Okay, right here. Let's differentiate implicitly. So when you do this, what you're going to do is you're going to take the derivative in respect to x of both sides. So let's take the derivative ddx of the left side, and let's take the derivative in respect to x of the right side. Because again, once in algebra and anything, no matter what level you're at, whatever you do to one side, you do to the other side. You guys know that. So we got to differentiate the left side, then differentiate the right side. Let's do the hard part first. What's the derivative of the constant?
0.
Okay, that was the hard part. Okay, so the right side 0. Okay, now let's differentiate the left side. Now, when you differentiate a sum, you just sum the derivatives. So you have to differentiate both of these. Derivative of x squared is simple. What's the derivative of x squared?
2x.
Okay, so you get 2x here, plus the derivative of y squared. Now, that's a chain rule. So derivative of y squared will give us first 2y times the derivative of y in respect to x, which we call y prime, and set that equal to 0. Okay, and now we wanted to find the slope of the tangent line at 3, -4, right here. Let me highlight what we want to do. Which means what we want to do is we want to isolate the y prime, solve for the y prime, solve for dy dx, and then evaluate this function in terms, or at that point 3, -4, but you should notice something different compared to what we did the first time. Let's isolate y prime first. Okay, so if you do that, subtract 2x, bring it on to the other side, and we get 2y y prime is equal to -2x. And then divide both sides by 2y, and you get y prime is equal to x, -x divided by y. Because the 2's cancel out. Now, in the beginning, when we found the slope of the tangent line, when we did it explicitly, we only needed to know x, the coordinate x. Look back up here. Let me go back, scroll up so you can see it. Look right here, in the upper right. We only needed to know what x was, because it was an explicit function. But notice the difference here. When we have this derivative, the derivative is not only in terms of x, but it's in terms of x and y. So you not only have to substitute the x coordinate in, but what? The y coordinate too. And that's a big difference between implicit differentiation and explicit, is that when you find the slope of the tangent line, you're going to have to put both x and y coordinates of the point in, not just the x coordinate. So right now what we need to do is we need to evaluate it at x equals 3 and y equals, what's y value at the point? Negative 4. And when you substitute those values in, we get negative 3 divided by negative 4, which is 3/4. And you'll compare that to the previous slope. Didn't we get 3/4 earlier? So whether you differentiate explicitly or implicitly, you get the same result, but you're going to have to learn how to do it implicitly, because sometimes you cannot solve for which variable?
Y.
For the y variable. And it's impossible. Like this next one, I wouldn't try to do it, because you'd be trying all day long, and you're not going to be able to do it. Even I couldn't do it. Okay, so in example number 2, we have the famous, oh, well, wait, this is not the one I was thinking of. Okay, we just have an implicit function here. It's a cubic function. And then a crazy one, you want to find the slope of the tangent line. Oh, you want to find the equation of the tangent line. So we're going to have to go further here. At that point, 1 comma negative 3, right here. This is 1 comma negative 3, and here's your tangent line. So to find the equation, we're going to have to find our slope first, and then after we know the slope, we can use that in the point to find the equation. It's actually pretty straightforward. Okay, we're going to have to do it implicitly, okay, because it's impossible in this case to solve for y. So here we go. We're going to take the derivative of both sides in respect to x. Okay. And we're going to assume that y is a function of x here. So anytime you take the derivative of a variable involving y, you're going to have a y prime involved, because you're going to have to kick in your chain rule every single time. So let's do it together here. The derivative of y cubed in respect to x would be what first? Using the power rule.
2y squared.
Okay, 3y squared. Okay, there's your power rule. Times the derivative of the inside function y. Y prime. Okay, so times y prime there. Now we got to differentiate the y squared, so plus. Okay, 2y times y prime, and then minus what? Minus 5 times y prime. Okay, and then, well, just differentiate your x squared to get, be careful. Yeah, just minus 2x there. Derivative of x squared in respect to x is just 2x. And then that right side is derivative of the constant? 0. Okay? Okay, now to find the slope of the tangent line, it involves evaluating the derivative at that point. And so what you want to do is isolate y prime in at this point here. Actually, you have, well, I'll hold my comment until later. Let's isolate y prime. So let's shift this 2x term over to here to the right. And y prime's involved in the first 3 terms. It's here, here, and here. So let's factor it out. So you're going to have y prime of times the quantity 3y squared plus 2y minus 5, all set equal to 2x. Just distribute out the y prime so you can isolate it. Because remember, to find the slope of the tangent line, you have to evaluate the derivative, which means you got to solve for the y prime, or the dy dx. Divide that whole thing by that quantity there, and you have y prime is equal to 2x divided by that whole thing. Give me a thumbs up if you're with me on the algebra there. You guys jump in with questions as we go. Okay, don't wait. Now notice the derivative is in terms of x and y. So at our point here, look in the left side here, x is equal to 1, and x is 1, and y is negative 3. we need to evaluate that at x equals 1 and y equals -3. So everywhere you see an x, you put a 1. Everywhere you see a y, you put a -3, and you get a slope. This is going to give us the slope of the tangent line at that point. So let's see what we get. If we put a 1 in the numerator, in for x, we get a 2. And you see over here we get a 3 times 9, plus a 2 times -3, and then a -5. What is that? So 27 minus 6, 21. 21 minus 5 is 16. Anybody else coming up with 16?
Yeah.
Okay, 2/16? 1/8. So this is 1/8. And that represents the slope of the tangent line. Okay, but we want not only this, we don't want the slope of the tangent line. If you read the directions, we want the equation. So now what we do is we kick in your point slope form, which is y minus y1 equals m times x minus x1, and we get our tangent line. So we're going to use this point, and we're going to use our slope of 1/8, and we're going to substitute both of those in there at the same time and get our equation. So what do we have? We have y minus a -3, which becomes y plus 3, is equal to 1/8 times x minus 1. And let me see, what do we get? Y equals 1/8 x minus 1/8 minus 3. Y equals 1/8 x minus 3 1/8. You guys know what 3 1/8 is as a decimal, approximately?
3.1.
Yeah, it's 0.125. It's 1/8 is 0.125. So it's the y-intercept here is at -3.125, and look right here. Could that be -3 1/8 right here? It's a little beyond -3, right? Oh, is that a different graph? What am I doing? I got to go up to the top. Oh, right here. There's -3 right here. Does that look better?
Yeah.
Got to point at the right graph, and then.
All right.
Okay. That's better. And by the way, the slope's 1/8. Is that shallow or steep?
Shallow.
Up 1, right 8. Shallow or steep?
Shallow.
Yeah, I mean, you only go up 1 unit and then run 8. This is a slope of 1/8. It's pretty shallow. So the results are making sense. The slope of 1/8 makes sense. The y-intercept makes sense. You know you're looking good. The only problem is you couldn't check this on the calculator. Eyes up here. On a T84, you'd have to isolate y there. So only certain graphing programs and certain calculators can handle implicit functions. So checking this on your T84 would be pretty much impossible. Okay? Okay. All right. So let's let's have you try one here. Let's turn the page, and let's try the famous lemniscate, one we saw last semester. But you know, I'll tell you what, we'll do this one together here. Okay, so on the lemniscate here, we've got a composition right here. This is a chain rule. And then right here, we have a product, so we're going to have to kick in our product rule. So we got a lot going on in this example here. It's not as easy as one looks, or as it looks like. And in the end, what we want to do is find the equation of the tangent line at 3, -1, or 3, 1. So don't try to isolate y. That would be pretty difficult. Let's do it the implicit way. Okay, so let's take the derivative of both sides first in respect to x. And keep in mind we got a chain rule on the left and a product rule on the right. Okay? You guys ready?
Let's do it.
All right. Okay, so what we do first is we start differentiating the outer function, which is the squaring function. So now we have the power rule. So we're going to have 3 times 2. You know, what's 3 times 2 to something to the 2 minus 1 power, which is going to be the first power in a minute. All right, times the derivative of the or evaluated at the inside function, x squared plus y squared, times the derivative of the inside function. I'm going to step this one out for you, because this is not as easy as it looks. Okay, right here, when you take the derivative of x squared plus y squared, that right there is going to be, you know, the sum of two derivatives. The first one's easy. All right, and be careful here on the y squared. We're assuming that y is a function of x there, so that requires a chain rule again. Okay, and then we'll evaluate that in a minute. So let's work on the right side. This is a product. In fact, if you guys wanted to, is it legal to take that 100 and bring it out?
Yep.
You could think of it that way. So you could think of it like this: 100 times something. Okay, where the first function is x and the second function is y. That's probably one of the easier ways to think about it. So here we go. Let's do it together here. Let's differentiate x first. So the derivative of x is 1. So first function times the derivative of the second. Okay, so what's the derivative of y in respect to x? Y prime. So it's going to be x times y prime plus second function y times the derivative of the first function, which is x. And the derivative of x is just 1. So that was actually pretty simple. Okay, so the right side's done. Now we got to work on the left side a little bit. We're going to have 6. Let's clean it up a little bit. 6 times quantity x squared plus y squared. And now we got to multiply it by the derivative. All that in red here. So everybody eyes on the yellow stuff here. Okay, so distributing through the derivative. Derivative of x squared. Okay, plus derivative of y squared in respect to x. Here's the chain rule. So the derivative of y squared initially gives you 2y times the derivative of y in respect to x.
Y prime.
Y prime. Okay, equals 100. I'm going to distribute through. 100x y prime plus 100y. Okay, now let's pause here for a second here and remember what we're doing. We're trying to find the equation of the tangent line, which requires us to find the slope. So you have two choices. Bring your eyes up here so I can talk about it, because one's easier than the other. We have a choice of isolating y prime like we did on the previous example, and evaluating, having y prime equal something, and then evaluate the derivative at, 3, 1, which means x is 3 and y is 1. We can do the same thing. Or we could substitute x equals 3, or 3 in for x, and y equals 1. Right now, everywhere we see x, we put 3. Everywhere we see y, we put 1. And then isolate y prime. You can actually substitute in your point before you isolate the derivative. So what do you think is easier? Isolating y prime now with dealing with variables everywhere? Or do you want to substitute the numbers in and just deal with a bunch of numbers?
Substitute the numbers in Ainsworth.
We'll do that first. Substitute in first. Okay. You're going to find out that you make less mistakes probably doing it first. So substitute in, sub in or 3 in for x, or x equals 3, and then y equals 1. That's this point right here, guys. All right, into the equation and go for it. So let's try it. And we got 6 times, 3 squared is 9, 1 squared is 1. Okay, and then you got 2 times 3 is 6, plus 2 times 1 times y prime is equal to 100 times 3 times y prime plus 100. There we go. And we just got to simplify that and isolate y prime and we get our slope. So let's see here. We got 60 here. 6 times 10 is 60, and distribute that through. So 60 times 6. 60 times 6.
360.
Okay, so 360, and then we got 60 times 2, 120 y prime is equal to 300 y prime plus 100. Okay, we got to gather the y primes. Got to have y. We want y prime equal something. So subtract 120 from 300. What's that?
180.
So 180 y prime here. Subtract 100 from 360. You get 260. And then divide by 180, and we're done with a slope. But what's that? Cancel out the leading zeros. What's 26/18?
13
9. Okay, so 13/9. We got 13/9 is equal to y prime. Guess what that represents? The slope of what? The slope of the tangent line. Okay, so there's your slope. And now what you need to do is use that in your point to find the equation. So let's go back way up here and let's work it out where we have some more room up here. Who's following pretty well so far? Be honest with me. Okay, good. Okay, so then we just use your point slope form. So y minus what? Help me out a little bit. It's y minus y1.
Y minus 1.
See, this one's x1 and this one's y1. We're substituting our point in, so y minus 1 equals slope 13/9 times x minus 3. And there's your tangent line right there in point slope form. So
Should we simplify that?
you should get, y equals something. So, you just distribute through, right? So you have 13/9 x minus 39/9 plus 1. Now 1 is 9/9, so what's negative 39/9 plus 9/9? Negative 39. So our final result is 13/9 x minus 39. How many times does 9 divide into 30?
Doesn't like 3.5.
3 and what?
A third.
3 1/3 times. So negative 3 1/3. Look down here. Look at the y-intercept. Negative 3 1/3. See, it makes sense. And not only that, the slope makes sense too because it's pretty steep. Up 13, right 9. So things are making sense according to the graph. Okay. Let's do this. We have time for you to try something here. Let me have you work on this one.
Angler, come on, man.
We got quotient rules and product rules on this one.
Good Lord, baby Jesus, dude.
I know. I'm gonna.
How can we approach this?
Well, quotient rule, right? The first one's a quotient rule. The second one's a quotient rule.
Product rule.
On the right side, you got a product rule and a constant.
Let's do this, Angler. Bring it on.
Who's hungry in here?
I'm hungry, Ainsworth.
All right. I'm gonna pause the video here. Okay, I'm going to use the quotient rule first, so everybody eyes on your first fraction here. Okay? I'm going to use the quotient rule at this point. So low D high, so I've got y squared times the derivative of 3x squared, which is just 6x. Okay, minus, low D high minus high D low. So, what did I just say? 3x squared times the derivative of y squared, which is 2y times what? Y prime, all divided by low squared, which would be y to the 4th. Okay, that's the derivative of the first fraction. Who got that right? All right. Okay, now watch this. Next one. Okay, I put in quantity because you're subtracting a quantity. Okay, here's the quotient rule on the second fraction in blue. Okay, so low D high, so x squared times the derivative of y squared, which is 2y y prime, all right, minus high, which is y squared. Okay, now let's finish this problem up on this. Let me see, in the second part here we got y squared times the derivative of 2x, which is simply 2x, all divided by low squared, or x to the 4th. And that's going to be equal to the derivative of the right side, which is going to involve a product rule here. So eyes on the right side on xy squared. I need to differentiate that using what's called the product rule. This part's going to be, let me see, I'll put it in green this time. This part's in green. Okay, now on the right hand side we got a product rule. X times y squared is a product. Derivative of the constant there is going to be 0, so just focus your eyes on your x times y squared, and you got first function x times the derivative of y squared, which is 2y times y prime, plus second function y squared times the derivative of first function x, and that's 1. Okay? And then the derivative of the constant gives you 0. So derivative of negative 29/4 is 0, so we don't have to worry about that. Now this is a very complicated expression, and isolating y prime is difficult. So what we're going to do is we're going to substitute in our points first. Substitute in x equals 1 and y equals 2 first. Sub in x equals 1 and y equals 2 first before you isolate y prime. Before isolating, y prime. So let's go ahead and do that. I'm going to, everywhere I see y, I'm going to put a 2. So I've got 2 squared times 6 times 1 minus 3 times 1 squared times 2 times 3, times 2 times y prime there, all divided by 2 to the 4th, minus, 1 squared, so we have 1 squared is 1 times 2, so 1 times 2 times 2, so y is 2 there, times y prime, minus 2 squared times 2 times 1, all divided by 1 to the 4th. And then again, we got the leading 2 there on the right side, times x equals 1, times 2, y is 2, times y prime, plus 2 squared. And we just simplify. So let's see here, we got 4 times 6 is 24, minus, we got 4 times 3 is 12, so 12y prime, all divided by 16.
Hey, we were going to talk about that problem today.
On the second quantity here, I've got 4 y prime minus, let's say 4 times 2 is 6, 4 times 2 is 8, divided by 1 of the 4, which is 1, is equal to 4y prime plus 4. And what we need to do is just simplify all this. So I'm going to split the fraction here, so we get 24/16, which is 3/2, minus 12/16, which is, 4 and that's 3/4 y prime, distributing through, minus 4y prime plus 8 is equal to 4 y prime plus 4. And what we need to do is isolate the y prime. So, let's see here, I've got, let me see, 1.5 plus 8, let me see, that's 9.5, and then I got to subtract that 4 on that side, so 9.5 minus 8, 9.5 minus 4 is 5.5, so that's going to be on my left side. When I combine this right here, I get a negative 4 and 3/4. When I add it to the other side, I get 4 and 3/4 plus the 4, which is 8 and 3/4 here, times y prime. You can step it out if you'd like. And now I've got to change to mixed here, so 4 times 8, 32, plus 3 is 35/4. So we got 11/2 is equal to 35/4 y prime. Multiplied by the reciprocal, y prime is equal to my 11/2 times the reciprocal of 35/4, which is 4/35. And I've got, let's cancel here first, 22/35 for my end results, and that's the slope of the tangent line. Okay, now to get the equation, all I do is substitute it in. So to get my equation here, I need to substitute in my points of form, y minus y1 equals m times x minus x1. My point for substitution is at the very top here. It's 1, 2. So I'm going to just write that down, 1, 2. So I get y minus 2 is equal to my slope, 22/35, times x minus 1. When I distribute through and add 2 to it, I get 22/35 x minus 22/35 plus 2. And my result is 22/35 x. 2 minus 22/35 is 1, and 13/35. So plus 1 and 13/35. And there's your tangent line right here, which is what you want. All right, there's my end result. All right, so give that a shot. Give your homework a shot in your book, and we'll try the attached problems in class and get some extra practice with them. Good luck. See you tomorrow.